I will talk about what I perceive as important connections between jet quenching, transport, and flow. Okay. So now it's working. And I would like to start with a helicopter view before I go to specific problems. So imagine just for a moment that end of this century, there's an ultimate textbook of QCD on the shelves of some library. And it contains a chapter on heavy ion collisions. That's why we are here. So how do we write this chapter? What do we emphasize, and what is missing for this chapter to be written? The natural emphasis in any textbook is on what we see, what is numerically large and what is generic. And we have two phenomena that are really numerically large, generic in heavy ion physics over all the energies. The one is flow, the generic low PT phenomenon, seen essentially all multi-particle soft hadron production process in heavy ion collisions. The other is jet quenching, the generic high PT phenomenon, seen essentially in all high PT hadron production process in heavy ion collisions. To zeroth order, both are deviations from a free streaming and fragmentation baseline. They are deviations from that picture that will appear in the proton-proton collision chapter of that textbook. Now, we can ask based on that, what can we talk about? Clearly, the book contains also a proton-proton chapter. And this chapter is currently based on that picture that is based on free streaming plus fragmentation. Different chapters must be connected to each other. So either perfect fluidity is understood as emerging with increasing system size, energy density from a close to free streaming picture, or the close to free streaming picture is not a valid starting point in the smallest collision systems. Clearly, the book is written in the language of quantum field theory, and quantum field theory doesn't have separate words for the partons in the jet and the partons in the medium. So would be nice to have an encompassing dynamics that doesn't make a sharp split between a fluid and a jet. Also, clearly, we can go in many of the observations that are shown in these meetings and ask whether our most elementary interpretations even require better demonstration before making textbook. For instance, if we invoke final state interactions these final state interactions must also show up in some jet quenching. It's a quantitative question then. So for me, the question why we see a significant flow in the smallest collision systems, while the nuclear modification factor is consistent with zero within large experimental and systematic uncertainties, is something we have to explain quantitatively. Now, all these motivations are fine, but now we have to be a bit more specific. And I first comment on transport versus flow. Quite generally, this is to outreach for this audience. We characterize medium properties in textbooks by response functions. Here, this is a response function that measures how the energy momentum tensor that we imprint in different collision geometries responds with respect to perturbations. And we measure such response functions indirectly, for instance, via flow. What we know about the analytical structure of these response functions is that in the analytical structure of the Fourier transform of these response functions, we can read off the medium properties. In the simplest case, if we excite something, the excitation decays. And the way the excitation decays has a height can decay via hydrodynamic mode. That would be a sound attenuation length. depending on the wave number, the inverse wavelength. And there can be non-hydrodynamic decay modes. We know that in all quantum field theories, hydrodynamic excitations are universal. They are a direct consequence of conservation laws. They are described by the gradient expansion, irrespective of whether we talk about a strongly coupled plasma or a QGP, they are there. The non-hydrodynamic modes, what do we know about them? We know that there is no quantum field theory without such non-hydrodynamic modes, so we must be able to talk about them. They are a direct consequence of causality. They are not described by a gradient expansion. So it would be nice in that textbook to talk at least about the distance between the hydrodynamic and the non-hydrodynamic poles in order to say how hydrodynamic we are and to say on what scale non-hydrodynamic modes kick in. It would be ideal to talk also about what we know in QCD about these non-hydrodynamic modes that must be there because QCD is a field theory. The recent revolution in Bayesian inference methods is not only a resolution in precision as it has been presented. It's also, due to this precision, the first time that we get access to some aspects of these non-hydrodynamic modes. In particular, go into this particular fit and you read off not only eta over S we know and love, you read off also this tau pi, which in Israel's Stewart model sets you the depth, that means the decay rate of the non-hydrodynamic excitation that is in Israel's Stewart. So in contrast to 20 years ago, we can not only confirm that the value of eta S extracted is a perfect liquid in the pure back of the envelope argument that the expansion is close to an isentropic one. We can also ask now up to which wavelength the excitations we propagate in this medium are really propagated by hydrodynamic modes or non-hydrodynamic modes. The requirement is that the pole is much closer to the real axis, the hydrodynamic mode, than the non-hydrodynamic mode. And if you put the numbers of the Bayesian inference methods in, you find that the wavelength for this to happen must be much larger than 1 Fermi. So this Bayesian inference method informs me that there is no such mode that fits into a proton collision system, and that it's in fact difficult to get such long wavelengths into at least peripheral or semi-peripheral heavy ion collisions. This is a direct argument that even if hydrodynamic modeling works to some extent in our Bayesian inference, we are getting our nodes into a situation that in the medium is more than hydrodynamic. To put this parametrically on the page, imagine a system of size R. It can maintain a smallest wave number of size 1 over R. And it can propagate parametrically over the longest propagation time of order R. That is the case. So if you go again in with a knowledge of what's the parametric dependence of a hydrodynamic and of a non-hydrodynamic mode, you will find that as you decrease R, the non-hydrodynamic mode becomes parametrically more important. The hydrodynamic mode becomes less important. And the numbers I've read off from Bayesian inference tells me this is relevant for the non-central heavy ion collisions we have. We have spent quite some time to support this picture by taking transport theories, simplified transport theories that interpolate between free streaming, the model of proton-proton collisions, and perfect liquidity, the current model of heavy ion collisions, to show that the nature of non-hydrodynamic modes, even if they are displaced by the same distance, even the nature affects the collective flow we see. This is not the topic of this talk, but just to put as a starting point that taking results of modern Bayesian inference studies seriously reveals the importance of non-hydrodynamic modes in kinetic theory, while kinetic theory is a possibility to interface free streaming the proton-proton picture with a heavy ion picture. Now let me come to the other leg, jet quenching. And to put it blatantly, jet quenching is a peculiar kinetic transport. I could speak an entire hour about what is peculiar about this. But essentially, kinetic theory transport is not billiard ball physics. There are formation times in this system. Jet quenching is just, in all these models, an evolution of this kind with 2-to-2 collisional, we say, and 1-to-2 radiative, we say, splittings. And what is peculiar in the BDMPS, Sid, Julashi, Wong, etc., picture is the soft gluons come first. Why? While in the vacuum, they come last. It's no coincidence that the people who wrote these models 20 years ago, Bayer, Müller, Schiff, Son, were the people who had formulated bottom-up thermalization. They realized already then that it's the same dynamics. In fact, we have numerical evidence that's not on phenomenologically relevant scales, that if we put up a single hard component and we let that this distribution of single hard components fragments, they hydrodynamize quickly, and they hydrodynamize by going from an overoccupied system first to an underoccupied system where kinetic theory matters, and only then relaxing to hydrodynamics. We know this for 20 years. We know in some sense that the QCD effective kinetic theory incorporates jet quenching and flow. It is a more encompassing heavy ion paradigm than the perfect liquid. So I put out all these words, but now this is a dedicated workshop. Let me come to a specific question. I have how many minutes? 15? Perfect. So the idea clearly must be, if one has such a picture, to support it in different ways. We have at CERN in different collaborations attacked this by looking at different problems in transport theory in recent years. We have looked at different questions of small systems to understand the interface between flow and why nuclear modification factors do not show up. Here I show another idea that goes into the same vein. The specific question is, what is testable about a perturbative picture of QCD effective kinetic theory, given that at some scale, non-perturbative physics effects will always be there and obscure the fact. And one could ask whether chemical accumulation is one such way. Now you could say that is already Rafalski, Müller, Koch, 1980s. They entertained Bluetooth SS bar, but we know by 30, 40 years of physics that Bluetooth SS bar has also a lot of hadronization effects. You don't know whether your counts come from the quark-gluon plasma or from the hadron case. But at LHC energies, it may be interesting to consider the splitting function Bluetooth CC bar. Can we measure increased CC bar production due to final state interactions? Can we measure a transport effect there? Now, if you think about that, first of all, there is a problem. We know from the PP part of that famous textbook that heavy quark production is perturbatively calculable. To be specific, if you calculate a hard process with a standard collinear factorized approach, most of the phase space open for CC bar production will be close to back. The invariant mass of the CC bar pair is of the order, say, of the partonic center of mass energy. It's much larger than 4mc squared, and that is larger than any scale that the medium provides you, would be its temperature or saturation scale. So this production is so short distance that it's unaffected by the medium. It's the short distance piece. And this is known to dominate the rate. In this situation, you don't change the rate of CC bar. What is long distance is a C and a C bar that go out into the medium. And the dominant medium modification of the process is a reshuffling of the C and the C bar in phase space. In a BDMPS kind of approach, that would be mediated by heavy quark energy loss. You test with these problems, C to C glue, but not glue to CC bar. But there is another piece. If you go to the first next to leading order calculation of heavy quark production in the 1980s, Keith Ellis and collaborator, they were curious about this so-called collinear limit of QCD. They tested in their calculation that at next to leading order, if you could look at CC bar plus X, and I write it here for the gluon-gluon channel, if the invariant mass is much smaller than the partonic center of mass scale, then the cross-section automatically factorize into the cross-section of a gluon production, so a gluon jet, so to say, that splits into a CC bar. That is the long distance part of the process. And we know, and they wrote it already in the 80s, that this long distance part needs resummation. That's the start of the parton shower for this particular process. Now, you will have gluons here that have a high transverse energy. And you can single them out. That is then just, this cross-section is then just a gluon jet. And these gluons will be boosted with respect to the rest frame. The boost is parametrically the gluon energy over the mass of that object, so Eg over Q. So if you choose Eg large enough, the CC bar production point will be boosted far enough. And that means you are now in a situation that is consistent with the PP chapter, but that should give a medium modification. The phase space for Q squared, much smaller than S hat, is very small. As a consequence, the total rate is almost unaffected. This is a power law suppressed contribution to the leading ones. However, you can single out this contribution by looking for your CC bar pairs inside jets. So what we wanted to do, we wanted to get insight into the possible rate that our understanding of QCD effective kinetic theory predicts for this particular chemical transport phenomenon that can be observed inside jets. And the advantage of a C and a C bar is that you are not completely dominated by hadronization dirt at the end, either by D0 bar, on which I will focus, or by semi-leptonic decay processes. If the eyes of Gunther look favorably with this respect, one may hope to get a distinct counting device that counts these objects inside a jet. So what we did our own calculation of glue to CC bar. This is a calculation that follows in the footstep of the entire morning section. You will recognize many of the elements here. And in fact, coming from a strange angle and not having read all the not read all the recent literature that has been presented here this morning, we had a glitch in the first version that was kindly pointed out to us, that was repaired before quark matter. But we have also some misrepresentations in the introduction part of that we are still trying to get faithfully there, so that our text reflects also in the introduction the current technical state of the art. And we apologize to all those, not only here, but others, that were missed in the first list of references. In any case, what is specific about the glue to CC bar is that the full set dependence can be given to leading order in NC in a differential way that involves only this dipole cross-section and not some higher order terms. And in fact, the expression as written here contains a subleading NC piece that makes sure that not the differential expression, but the integrated expression is correct to all orders in NC. So what are the physics properties? I don't go into the technicalities of deriving that. The physics properties, if you switch off the medium, you get the glue to CC bar vacuum splitting, where the virtuality takes this eigenal expression form. If you go into this expression, you can look at the interplay between totally coherent and incoherent production limit. And in this way, you get from the calculation rather than from your words, the formation time that I used to motivate that boost. So this characteristic E over G times 1 over Q with a prefactor 2 in the calculation. If you ask what is the absolute scale at which glue to CC bar becomes numerically important, the calculation reveals that the scale is that the average momentum transfer squared picked up by this collision system is of order of the charm mass squared. So Q hat integrated over the entire length. If that object is of the order of mc squared, then the effect becomes numerically sizable of order 1. And that is realized if you take the values of Q hat that you extract from jet quenching models seriously. That is phenomenologically in the cards. That's also the reason why we focus at the moment at CC bar and not at BB bar. Clearly for BB bar, everything else goes through, but this parametric estimate does not go through. It's less favorable for BB bar. So we will have less than 10%. I throw a number in here of effects. The calculation also reveals what everyone knows on theoretical grounds, but here you have no singularity, so you integrate over and prove it, namely that this is a higher twist effect. The medium modification doesn't lead to an additional logarithmic enhancement. It's a power suppressed but numerically large, since geometrically enhanced contribution. With this said, here is one characteristic result for the splitting function. We show the splitting function times 1 over Q squared because all the Q squared parts that show up in the Sudakov factor receive medium modifications. And what you see is that compared to the vacuum baseline, there is a characteristic enhancement of the CC bar pairs at a scale set by Q hat L. What you see is that at the smallest transverse momenta, the distribution can be depleted. That's an effect of momentum broadening. Almost collinear processes are shifted to larger angle. And what you see visually is that if you integrate over that, there is a significant effect that remains. The enhancement in this particular case are of the order 60–70% in a wide phase space region. The envisaged experimental strategy that we considered as a first step is to ask if we go into a typical jet reconstructed in heavy ion collisions with R equals 0.4 anti-KT jet, can we count the D0 and D0 bar pairs in that jet and simply look at the number of these jets? If we ask how many counts there are there for a luminosity that is expected for HL-LHC, so the proton-proton equivalent of 10 inverse nanobarn is put into Pythia, you see that for such a yield events, we would get 10 to the 8 counts in the 20 GeV region, 10 to the 6 counts in the 80 GeV region. Then you would have to fold in the experimental ability to detect them, the branching ratios. So there are killing factors here. But there is the idea from this number certainly that out to 80 GeV or so, this could be in the cards if this is possible. Then we can ask about the vacuum baseline. So that is the number of D0 bar pairs per jet. So in one of every 50 jets, say for that jet PT, there is a D0 bar pair in a vacuum production. And I should say this line is already textbook physics. So in the late 1980s, people were interested in understanding in a parton shower the virtuality distribution. Can I really see which fraction of my parton shower was above a certain resolution scale? There is, in the context of the so-called modified leading logarithmic approximations, there is beautiful work of Al Müller, of Paulo Nasson, of others that have essentially shown such plots, and they have even shown to what extent these could be used with a poor knowledge of that time to determine whether the charm mass is 1.7 or 1.3 GeV. So it's a direct luminosity meter. This is the last plot. I don't go over time. Then clearly in a heavy ion experiment, you have the problem that your energy is not controlled if you don't tag it. This dashed line is an estimate of what happens if you take that rate, but your energy scale shifts due to out of cone radiation. That needs to be tested, but what we see is that for the estimates we have, the calculated effect obtained by reweighting of a parton shower with the medium modified splitting function we have calculated should be visible about this. So there is this question whether a measurement of this kind could be the very first step of perturbative chemical transport theory. And I should say, there are many ways of going differential. When I heard Xin Yang's question in the last session, it's clear we looked with flavor cone at the ability to see the two cbar prongs in the environment to do this more differential. Then it's clear one is sensitive to this formation time. But first of all, we want to put out a statement about the yield. So there's more to come, hopefully, in this direction. And all I can do is I thank my collaborators on that, and I say stay tuned. Thank you.
Now we have time for questions.
Could you just go back to the previous slide? So do I interpret the little insert there that the most prominent effect would be at around, I don't know, 30 GeV or so? So I mean, I just want to make sure I don't.
Yes, I mean that is numerically the largest enhancement. Then clearly one will have to fold in an experimental assessment. You see, if you tell me that experimentally you measure, you are much more comfortable about this regime, and you beat the somewhat smaller effect there, then that is the better way. But numerically, the largest deviation we see here is clearly around 20-30 GeV. And the reason why it decays slowly is at some stage, so the physics effect here is as your energy gets higher and higher, your cbar pair starts being boosted to such an extent that the medium doesn't affect anymore the splitting rate. So as our calculation knows about formation time effects, it's clear that in the ultra high energy limit, again, we start dying out, but the dying out is a very shallow power law dying out.
Maybe I should ask it in the break, but could you explain again what the gray band there represents?
The gray band, I think, is folding in the red band. Look, I mean, okay. The red band is the variation between, sorry? So what we do is we read through the literature, what are the values for the extracted from models for the quenching parameter Q hat. There is a time dependence on that quenching parameter. It's amazing actually by how much we are a little bit conservative by how much these values can vary if you take the multiply by L. And to be absolute sure to encompass from tech HQM to Jetscape to our own fits that we did during the oxygen exercise, to incorporate everything, we plot the entire band. So everyone who has put out a value on Q hat in recent year will feel comfortable to have this in this wide band. That I should be more precise. The precise value of Q hat is of course known better than a value between 1 and 8. But if you fold it with the L dependence and the dynamic dependence, you get large uncertainties.
Hey, thanks, Urs, for this talk. I have a question on your plot of the yields of the D0 tech jets. Do you have any kind of angular resolution between the D and D0?
So we require that they fit, that they are both inside this R equals 0.4 anti-KT reconstructed jets.
Okay, so you don't have any kind of minimum restriction between the D and D0?
No.
Okay, thanks.
And in fact, one should say that there is, you see, you have, if you would do this with a jet finding algorithm, you have, of course, your C and cbar tag, and with flavor cone, for instance, as one way of reconstructing these objects with the knowledge about the charm, you don't require it. Okay.
Yeah, I have a question. So what would be the requirements from an operational point of view to make sure that the cbar, are really related to some splitting, medium use splitting? And do you put some cuts? What would be those cuts?
So I think the risk of a theorist answering this question is clearly that the answer is oversimplified. But taking this aside, it's clear that we look only at prompt charm contributions. So we assume that somehow charm that comes from BB bar going into is either small or can be eliminated via displaced vertices. We have no evidence that this is a big obstruction, but that's something we have not included in the origin plot. Okay. Then the question is, which detector do you need in order to measure this with which efficiency? And I think I shouldn't comment on this at that stage, but I see someone laughing if I would try. Thank you.
So it's a question similar to Yassine's. If I look at your diagrams, it looks like you're only considering leading charm. Is that correct? So this would be a hard gluon within the jet?
No, so this is overall all splitting. So it's the entire parton shower.
But within the jet cone, right? So I mean, there's a well-known, mechanism has been measured. I mean, there's CC bar all the way down, right? So gluons go into CC bar at every Z, and so you're going to have significant combinatorics. And how can you guarantee? I think similar to Yassine's question.
What do you mean by significant combinatorics?
Who tells you there's only one gluon going to CC bar within a jet?
Well, the ratio is relatively small. You see this already in the vacuum. Clearly, it would be a major. Can I go back here, or is this frozen? I tried the arrows, but they don't like anymore to go back.
Okay.
So I showed you. I read out that in that for the jets we look at. There is the value. I mean, it's in the vacuum. We talk 1 in 50 jets has 1 CC bar. Okay. So yes, you have cases with 2 or 3, and yes, there is combinatorics in these codes, but that will not dominate it. So in fact, looking at the rate between 1% and less than 1%, we concluded that for first effort, we don't have to discuss combinatorics here.
So the separate question, you've discussed yields, but it seems to me a more direct, or a direct, we'll put a qualifier there, a direct measurement of kind of thermalization would be the angular correlation between. So CC bar comes with some, so a gluon goes to CC bar comes with some characteristic angular distribution, and if that is substantially disrupted, this I think would be a fairly direct signature.
So our calculation of the splitting function, of course, Yeah, how did why was I not able to do that? I'm amazed. So clearly on that level, I have to stay with the microphone, but on the level of the splitting function, you see we have access over the double differential distribution. So our Monte Carlo will also have access to that. Then the question is, what do you do first as a theorist? As a theorist, the integrated quantity is the most robust one. So you put it out first, and then you can dig into the more differential distributions. But this calculation, the Kc dependence here is correct to leading order in 1/nc squared, as said, so up to 10%, and the leading order in alpha s. That tells you where in phase space these objects arise. In fact, you can use this plot in order to make cuts on formation times. It is one way of assessing differentially as a function of transverse momentum in the final state, whether you were working with a short or a long formation time, and you expect for the two configurations different effects. So that would be a direct example for the question Xinyan raised, and we looked already into that. But first things first, and for a theorist, you go for the most robust quantity first.
Yeah, let me follow up on this. This essentially is what we consider non-equilibrium contribution to charm production, right? Brent and I actually did this estimate, what we call pre-equilibrium, but that's overall when the miniature thermalize, and we did that calculation, and we still have to wait to see whether that's the case at LAC energy or in the future, right? But for the same mechanism, in fact, I think maybe this is the same, but we did actually some estimate, not by looking at splitting, but rather in the transport model, we look at the collision between the jet shower pattern with the thermal medium. And that can produce another pair through gluon fusion, for example. Except that there's no interference, like sort of like angular structure, but in principle, this could be the same mechanism. But on the order of magnitude, we also find out, I think maybe we all can confirm if he's still in the audience online, we get like, 10-20% enhancement too.
Yeah, so we took note of at least one of your papers on that. Certainly this, the way we have set up this problem is clearly a setup in which if BDMPS set times calculations are the right way of doing pattern energy loss, this is a must, and the scale of the effect is penciled in. So in this sense, there is something useful. Also, clearly the calculation we do is quite more differential than what you have in this transport model, at least on the analytical side as a model. Clearly, there's always a differential aspect. So we think with this respect, it is different. I also have to emphasize that you get to the effect we discuss only by insisting that it is part of that jet. As I explained, if you would just look at a change of rate, I think you have a strong argument from QCD that this is a power suppressed correction that should be for the total yield smaller than any higher order correction that Cachari, Mangano, and the other high PT, high energy physics guys have not calculated yet. In other words, our calculation makes a statement about an enhanced heavy quark production without questioning that the perturbatively calculated heavy quark yield is a good baseline for heavy quark transport phenomenology. Okay. That's why I started the entire discussion with this factorized picture and saying which small phase space region you have to focus into in order to dig out this effect.
Can I ask a question?
Yeah, it's a question from Krishna online.
Thank you, Yenji. Hi, Urs. This is Krishna. Can you hear me?
Hi, Krishna. Good to hear you if I don't see you.
Glad to be there in a inadequate way. So my question is about it, using the diagram that you happen to have up on the slide right now, energy loss of that red gluon on the left. So before the gluon splits to CC bar, it loses energy in the medium, and we know that parton energy loss is the big effect, as you said at the beginning of your talk, or one of the two big effects in our field. So if I look at, let's say, a CC bar with 30 GeV and heavy ion, that in a jet in heavy ion, that CC bar with 30 GeV energy and heavy ion came from a gluon that started out with a higher PT than would have been the case in proton-proton, because the gluon lost energy. It lost energy in heavy ion in a way that it would not have done in PP. So in making the comparison, which you don't have to switch slides, but in making the comparison that you made at the very end between heavy ion and PP, how are you taking into account energy loss of the gluon before it splits and the consequent selection bias effects in making the comparison, the lead to PP comparison on the last slide of the talk?
Yeah, Krishna, that is a very important question. And you know, we have discussed this already, because you, in contrast of most of the audience, has seen the first draft of that letter we want to put out eventually. We have at the moment what we discussed with you shortly before quark matter. At that stage, we had an estimate that our reweighting technique will give the dominant effect. Also, it's very important to realize from the parametric side of view, we have control over the energy dependence of the effect. That means we know if that gluon would have lost part of its energy, we know that remarkably the splitting into CC bar would not go down, but it would go up. And that is so because essentially the formation time is then more favorable. But in order to put such discussion not only on the qualitative level as I do here, what we are currently doing, we are writing a toy Monte Carlo in which we interface this glue to CC bar with a glue to glue to simply have in the appendix of that letter a toy Monte Carlo that tells us that the estimates that we have provided to you prior to quark matter are realized if one does this with a simulation tool. Okay,
Thanks.
So stay tuned a little bit, and
right. So what we discussed before quark matter, which you just shared with everyone, is the question of how energy loss affects splitting. But I'm asking a different question here related, which is the energy loss means that the initial hard scattering had to produce a higher energy gluon in order to see that, let's say, 30 GeV. I'm just asking how you're doing how the selection effects are taken into account in the last plot of the talk, where you compare lead to PP.
Okay, so it's clear that you need to know the energy of the jet in order to know the vacuum baseline. Okay, and it's clear that if you lose parts, so in other words, so let me rephrase your question in a simplified form so that the picture stays. In the CC bar pair is not produced in the with high probability in the latest fragmentation, because it has a semi-hard, presents a semi-hard scale.
Right.
So it's produced relatively early in the parton shower of that jet. So if you would have the vacuum baseline, you would say there is a CC bar in that jet. I read out this rate, and that would be the black curve shown on the figure that I display here. Now, however, the soft gluons that are coming later are partly moved outside this jet cone up to pi, a feature of isotropization of the jet, also a feature actually of kinetic equilibration mechanisms seen in the data already. So you would quote then the number of CC bars with respect to a smaller jet energy, and that means a yield that you would see here at attribute a 50 GeV jet would show up as the yield of a 45 GeV jet. So in the figure I display, this is simply taken into account by assuming that, and that is this vanilla 10% that one sees in the data everywhere, by assuming that of the order of 10% was radiated out of the cone. Now, clearly you can do this more precisely if you have a simulation tool that gives you access to the transverse distribution. Clearly, you can say, for the purpose of our proposal, I would be able to devise observables that don't require it, namely by tagging the jet, for instance, by a C boson in the extreme case. Only then I kill so much the rate that this particular observable is not anymore in reach at HLLHC. So there are different ways of doing control measurements on that. I should warn that while we say a 10% energy loss is a standard value, nothing tells us that a jet with a cbar inside has an average fragmentation pattern in which 10% of the energy goes out of the cone. You can advance arguments that it looks differently if you require this inside a jet. So this is an educated estimate, 10%. And what we can just show at this stage is that the signatures that we calculate from the splitting function are significantly more enhanced than the typical uncertainties to the reconstructed jet energy that we would have to attribute.
So I have just a simple question, is it possible to come to an analytical expression for the G2 cbar splitting medium modified splitting function in some kinematical limits?
Say this again.
So is it possible to arrive at an analytical expression for this medium modified G2 cbar splitting function in some kinematical limits?
So clearly it depends on what you call analytical. Strictly speaking, this object that I display here is analytical. I have written it in ink. Yes, it contains a path integral. If you can expand this path integral in the simplest case in the opacity expansion. We have also some numerics actually that informs us to what extent first order of opacity captures at least some of the features if supplemented with a decent scattering potential, certainly not on the accuracy of what we have seen in other talks of this morning session. For me, the most important thing about these analytical approximations is not that they are the most precise ones, but that you get access to these physics properties that I have highlighted here. You can really read off what sets the length scales. You can read off what sets the absolute scale of the phenomenon. And you can confirm that there is no collinear enhanced piece that you would have to regulate. I mean, so yes, it is analytical, if that is your question.
Okay, so let's thank all the speakers in this section again.